for coming. It's a delight to be here this afternoon. Wonderful weather. Let's hope that the hurricane doesn't hit us. We'll keep it this way if we can. Yes, I've been studying the bottom of the ocean for about 40 years now, and I have on the door of my office at the university a cartoon from the New Yorker magazine. It's my favorite cartoon, so I'll let you take a look here. Ladies are sitting having tea, and one of them turns to her friend and says, "I don't know why I don't care about the bottom of the ocean, but I don't." So that's why I chose the topic for the talk today, is maybe try to convince people who might not care about the bottom of the ocean why they should. So 3 good reasons, maybe 4 in fact. Well, as you're probably aware, our planet is an ocean planet. 75% of the surface of the planet is covered with ocean water. This is a plot that shows you the elevation of the Earth's solid surface. Mountains and continental interiors take up about 30% of the surface of the planet, and the rest is covered by water. The average depth of the oceans is about 4 kilometers. And the deep sea trenches that you see depicted over here on the right-hand side of the screen are only maybe 5 or 6%, but they're fascinating places. And the thing is that now we can actually get to them. I was privileged to go out with James Cameron and his group on his expedition to the Mariana Trench in 2012, and we were able to see incredible things at these great depths in the oceans. So with all of these vehicles that we have now, both manned submersibles like the Alvin, and the Alvin is going to be able to go even deeper in its new version. The Japanese submersible 6500, Shinkai 6500, that can go to 6,500 meters. I've been in it to 6,499 meters. That was cool. James Cameron sub, the big green thing over here on the right-hand side, is the only vehicle that was able to go to the greatest depths of the ocean at almost 11,000 meters and stay there for a significant amount of time. The Trieste bathyscaphe dove to the Mariana Trench in 1960, but it just basically did a bounce dive. They had some problems with one of the windows that cracked while they were going down, and so they didn't stay too long. Came back up. Well, when Cameron dove, he was actually able to see the bottom of the Mariana Trench for about 2.5 hours while he was down there. But most of these vehicles go down for a fairly short time, a couple hours. The remotely operated vehicles can stay down a little longer, but basically these short visits aren't the answer. The trenches themselves comprise about 45% of the surface of the ocean floor. This is the depths below 6,000 meters. And a friend of mine here at the university, one of my biological colleagues, Jeff Drazen, says it's like trying to understand a mountain ecosystem by just looking at the summit. So imagine yourself dropped by super-powered helicopter on Mount Everest summit in the middle of the night with a flashlight, sitting there for 4 hours. How much are you going to see? How much are you going to learn? So what Cameron was able to do is take high-definition video while he was down at the Challenger Deep. And afterward, although he himself thought he didn't see much when he was there, one of my junior colleagues at Scripps Institution of Oceanography was able to take that video, analyze it very carefully, and she identified over 100 species of different animals, relatively small, but she could pick them out of the video, the high definition video he had, and she's published a paper on this recently. So there really are lots of animals that live down there in this incredibly dark, cold, and high pressure environment. So what are the problems for these deep sea organisms? Well, darkness for one. There's no light, so there are no photosynthetic organisms there for them to feed on, so there's not a lot of that sort of food. It's cold. The temperatures are from -1 Celsius to about 4 degrees Celsius. So the fatty membranes that outline our cells would solidify at those kinds of temperatures. So these animals use polyunsaturated fats, things like olive oil, or similar to olive oil, surrounding their cells. So these stay liquid at these cold temperatures and the pressures. The pressures are really the big problem. They're the elephant in the room. The pressure is about 6,000 pounds per square inch. So imagine you had elephants on pogo sticks all around your body, pressing in on your body at that sort of pressure. So it might be fun for the elephant, but it wouldn't be much fun for you. Okay, so how do these animals cope with pressure? The proteins in our cells are needed to break down food for energy, right? So they have to be able to change size and to change shape in order to perform their functions. This is hard to do under pressure. Jeff Drazen, my biological friend, said, okay, you can blow up a balloon in the air, but you just try to do that at the bottom of a swimming pool, and you'll see what the difference is. So how do these animals cope? Well, they take in things called piezolytes. These are small organic molecules that bind tightly to water molecules. And what this does is eventually it stops water from being forced into the cells by osmotic properties. So these are osmolytes too. The deeper an animal lives, the more of these piezolytes they take into their bodies, and this protects the cells from damage by pressure. An example of one of these is trimethylamine oxide, TMAO, and this is actually an enzyme that's used in medicine, that's used to treat Alzheimer's patients. It helps to protect the proteins in the brains of these people. But there's a limit for these animals, mainly for fish who bring this in. They can't take any more piezolytes into their cells beyond about 80 to 100 meters down, because then their cells start getting saltier. They get to the same salinity as the seawater around them anymore, and it starts bringing in the seawater into the cells, and the cells could burst. So we think there's a limit to the depth at which these animals can live. Here are some pictures of some of the animals we saw in 2014, November, December. I was back out in the Mariana Trench with the Schmidt Oceanographic Institute's ship, the Falkor. And if Hannah could give me a hand, I can show you some video of these animals. And this video will take you down depth and show you some of the animals that were videotaped on the arm of an autonomous lander that had a fish strapped to it to try to attract the animals. And this is fairly shallow. These, mostly those were rat tail fish. This is about 5,000 meters. These are large cusk eels that were attracted. We left this down, the lander down for a little longer than a day to try to get fish to come around. So this guy's trying to eat the PVC pipe as well as the fish. And these are two different types of fish, a rat tail and another cusk eel. This is a different variety of cusk eel that's ripping away at the fish on the bait arm. This is an amphipod, a crustacean that lives much deeper down. We first started seeing them, the real big ones, at about 6,000 meters. You'll notice that it has a sort of spiky tail. I'll show folks here in the room with this green laser pointer. But the large ones that were feeding on the bait would stick that back end of their body up, and you see the cusk eels are trying to eat them. Well, they have the armoring on their bodies, but they also have these sharp points on the back ends of their tails to keep the fish away. So now this is 7,000 meters, and you see mostly it's those crustaceans. And this is 7,485 meters, and these are snailfish. These are some of the deepest living fish in the oceans. And what you're seeing now in the bottom left-hand corner is a snailfish at 8145 meters. We got an image of the deepest fish anybody's ever seen when we were out on that cruise. Now, deeper still, all you're going to see are the amphipods at the deepest point in the Serena Deep, And this is just to the east of the Challenger Deep at over 10,000 meters. Thank you, Natalie. We could go back to the PowerPoint.
Cool. How big are those amphipods?
The biggest one is about, can reach about a foot in length, but most of the ones that you saw at the deepest part were a couple of inches or so. So let's take a look at that beautiful, deepest fish ever discovered. It has wonderful, delicate pectoral fins you see here, and it's fairly translucent. Unfortunately, we weren't able to capture one of those to see how it manages to survive at those kinds of depths. But the other snailfish that were brought up are being analyzed even now. Well, if we look at the amphipods, how are we going to capture those guys? On Cameron's cruise, we took a deep sea autonomous lander, the thing you see on the left, let it just descend to the bottom of the seafloor. And it had a boom arm that opened up and flattened itself out on the seafloor, and the guys on the ship grabbed chicken from the refrigerator in the galley and stuck it in the trap that you see on the bottom left, where all those amphipods are clustering around, and those guys stripped that chicken down to the bare bones in almost no time at all. So this is what the business end for defense looks like. These spikes that you see on the right-hand side of the back of the animal, and this guy is almost a foot long. The blue things you see are somebody's hands holding him once we brought him back up to the surface. And here's the amphipods in feeding position with their spiky tail ends up, trying to get that rat tail to leave them alone. And this is the business end that I would be afraid of. I used to like to think maybe I'd like to get buried at sea, because I'm a marine geologist now. I'm having second thoughts. We find other organisms on the seafloor. These organisms are feeding on the microbial subsurface population of organisms. You can see in the lower center part there are mussels. There are some snails and some galateid crabs and a few worm tubes. These are living at the top of a huge mud volcano very near the Mariana Trench. But it's a weird mud volcano. It's made up of actually mantle rocks that have interacted with fluid coming off the subducting Pacific plate, altered, and then been ground up on faults and rose to the surface of the seafloor and burped out to make a mud volcano that's about 2 kilometers high and 20 to 50 kilometers in diameter. These are huge, and they're famous now for the Mariana area. They also produce large chimneys of carbonate material, calcium carbonate, the same mineral that forms the coral that you see out here in Hanauma Bay. And this is a way that nature sequesters carbon dioxide. So if we can learn more about how this process occurs in nature, we can make efforts to sequester carbon dioxide by pumping carbonated hot fluids into exposures of mantle rock on the surface, a much more efficient way, perhaps, to extract carbon dioxide from the atmosphere and help to prevent global warming. So people are actually looking into this, and there are billions of tons of carbon dioxide that could be sequestered this way. Well, as we go deeper and deeper down the inner wall of the Mariana Trench, we find more of these cold seeps with organisms around them, all of them subsisting on this microbial subsurface community. At the deepest point in the Serena Deep, just south of Guam, to the east of the Challenger Deep, with the landers that we deployed on Cameron's cruise, we were able to see these mantle rocks covered with filaments of microbial mat. We call them bearded rocks because these filaments kind of looked like beards on the rocks, right? So these again are representative of these reactions that are taking place, fueling these microbial communities.